All right, so let's prove this bad boy. So for the first step, we'll show the equivalence of A and B. And this basically just comes from the way you write down matrix multiplication. So part B means, so to say that it has a basis of eigenvectors, that V has a basis of eigenvectors, this means that tvk is equal to lambda k vk for each of those vectors. And so if you write this in matrix form, then what you're seeing is that the matrix for T looks like this. Which is exactly what it says in A. And so that lest there be any doubt what's going on here is, like, if we take, say here's the matrix for T, and then we multiply it against the matrix for VK, so there's a 1 in the kth spot, then again this is going to give you a lambda k in that particular position. So this is exactly the meaning of T VK equals lambda k VK. Okay, so it's basically just a translation of it into matrix form. So now we'll do one of these round robin type affairs. So B implies C, C implies D, D implies E, E implies B, therefore they each imply each other. So we'll start with B, and so B says we've got a basis of eigenvectors. So let uj be the span of the jth eigenvector. And so then, since V is a basis, the hypothesis for B is telling us that V is the direct sum of these UJs. And since it's a basis of eigenvectors, it's telling us that each of these UJs is invariant under T. And then, since the lambda j are distinct, we then know that this is an orthogonal sum. By 538. Okay, so let's see then. Now we need to do C implies D. So if C implies, so for C implies D, let's see. So now we're assuming that we've got this direct sum decomposition into UKs, and since we're given that the dimension of each UK is 1, we know there's at least we know there's a non-zero element in each of these things, and so if we choose it, oh sorry, let's call it V. We choose VK in UK less 0. Then the fact that UK is invariant implies that that VK is an eigenvector. So UK is E lambda k. All right. That gives us D. Now to show that D implies E, well, this one actually, this is immediate from some old exercise. If you have a direct sum decomposition, then the dimension of the whole space is equal to the sum of the dimensions of the constituent parts. Okay. And then lastly, we do the hard part, which is going from E all the way back to B again. So for each of these eigenspaces, we're going to take, and I'm going to doubly index these. So Vj1 out through Vj, and then there's going to be we're going to take, this is supposed to be a basis for E lambda j. So how many things does it have in it? Well, it has the dimension of E lambda j, which I'll just denote by dj. That's the number of things that it has. So we're going to let this be a basis of E lambda j. So how many things are in that list? There are as many as the dimension of the lambda j eigenvalue. Okay. And then our hypothesis is that the sum of those dimensions is the dimension of the whole space. Okay. So then let's see. So we had a theorem once upon a time. It was 239 that says that if you have n independent vectors, then you have a basis. So it suffices to show that the collection of all these basis vectors from all the different EJs, or E lambda j's. So for E lambda 1, we have V1 1 through V1 D1. And then we have V2 1 through V2 D2, and so on and so forth, blah, 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 all the way down to VM1, VM, DM. Okay, and so just to make it clear again, so this is basis of E lambda 1. Then this next batch here, these are the ones that form the basis of E lambda 2, and so on and so forth, out to the basis of E lambda m. And so what we have from this previous line is that this list right here has n elements in total. Okay, so we want to show that we've got an n element list that's linearly independent. Okay. Whoops. Independent. Okay. So we do the usual thing, and we suppose that we have a linear combination. And so suppose we have the sum of AJK VJK equals 0. Okay, well, I can rearrange this sum so that it looks a little bit more pretty. So I'm going to collect them by whichever subspace they're in. So we're going to suppose that the sum and so then we'll have summing through the spaces J1 through M, the different eigenspaces. Within each space, we'll look at the sum K equals 1 through DJ of A JK V JK. Okay, that's slightly prettier. So suppose we have a dependence relation like so. Okay, then we can combine terms from the same eigenspace. And so this means then that we'll have, so we can say let uj be the sum k equals 1 to dj of just those terms that live in E lambda j. So that's just these ones. Okay. So this guy lives in E, whoops. So the linear combination of them lives in E lambda j as well. All right. So then, let's see. So then we have our summation from before becomes that the sum of the UJs is equal to 0. Right, so this one right here, well actually here, this right here is a UJ. So the sum of the UJs is equal to 0. All right, well, then that implies that each UJ is equal to 0 by 510, because we know that the eigenvalues for or the eigenvectors for different eigenvalues are independent. And then that implies then that since each uj is equal to 0, that tells us that the sum of the AJK VJK, each one of these is equal to 0. However, since those V's form a basis for E lambda J, they are linearly independent. And so that means that all of the AJKs are equal to 0. And that's what we needed to show in order to see that this is a linearly independent set. So we are done. And we have a brief corollary. So this is listed as 5.44 in the text. And that is that if we've got an operator and it has dim v distinct eigenvalues, so it has as many distinct eigenvalues as the dimension of the vector space V, then T is diagonalizable. And there's not really a need for proof for this. This is trivial. This is just 541 in the special case when m is equal to n.